In this video, we're going to talk about vector projections. Since we've investigated the dot product, we're going to apply it to finding the projection of one vector onto another, and then to finding the work done by a constant force acting through a displacement. The vector projection of some vector u equaling PQ onto a non-zero, and we'll call this vector V, which is PS. This is the vector PR, which is determined by dropping a perpendicular. So dropping a perpendicular down from the vector applied to the initial vector. So from Q to the line PS. So the notation for this, the projection of U onto V. So the way we are reading this is the vector projection of U onto some vector V. All right, if U represents the force, then this projection of U onto V represents the effective force in the direction of V. So I've brought in a picture to kind of help illustrate what we are looking at. We are projecting this force U onto the vector V. So if you think about it as, we're pulling a cart, and here's my cart, which already has this vector, and we're applying an additional force. So projecting U onto V, PQ onto PS, the effective force is created by PR. And we can visualize this in a second way. So if we look at this diagram that I've just brought in here, we still have U projected onto V. So U, PQ, is projected onto V, PS. But you'll notice that U is in the opposite direction. We still drop that perpendicular down and we create PR. That is my projection of U on to V. Again, we write that as the projection of U onto V. And I'd like you to notice two things. Notice here the angle theta between U and V was acute. In this case, the length, or that projection, was positive. But for our second diagram, the angle between U and V is obtuse, and we end up with a negative projection, or a negative length. So if U represents the force applied to V, then the projection of U onto V is the effective force. Looking at this picture, if we pull on the box with force U, the effective force moving the box forward in the direction V is the projection of U on to V. And to reiterate what I briefly said on the last screen, if theta, the angle between u and v, is acute, then my magnitude of the projection of u onto v is the magnitude of u times cosine theta in a direction of v divided by the magnitude of v. However, if theta, the angle between u and v, is obtuse, then my magnitude, the projection of u onto v, is negative the magnitude of u times cosine theta. And the direction associated with that vector is negative v over the magnitude of v. Now, in both cases, the projection of u onto v is going to be the product of that magnitude, which we said was the magnitude of u, cosine theta, times the direction v over the magnitude of v. And this is for the projection. That's the magnitude and direction of the projection, this product here. So let's think about developing our formula for the projection. I'm going to get a little tricky. I'm going to say the magnitude of u, and I'm going to throw in here, times the magnitude of v times the cosine of theta over the magnitude of v. And that's legal for me to do because I just multiplied by 1, putting that in there. Well, what we see in the numerator, that is now the dot product of u dot v. So this equals u dot v over the magnitude of v times v over the magnitude of v, which can be simplified into u dot v over the magnitude of v squared times v. So I'm going to pull in a more formal definition for the projection here. So by that derivation we just created, we can define the projection of u onto the vector v as u dot v divided by the magnitude of v squared, then multiplied times v. And the scalar component of u is always going to be this u cosine theta. And that can be defined in two ways: u dot v divided by the magnitude of v, or u dot the magnitude of v. And v divided by the magnitude of v is a unit vector for v. So it is u dot the unit vector for v. And so you'll see these are just illustrating again that we have an acute angle. We get positive magnitude of u cosine v for the length of that projection. And then the length of the projection when theta is obtuse is negative magnitude of u times cosine theta. Please note that both the vector projection of u onto v and the scalar component of u in the direction of v depend only on the direction of the vector v and not its length. Because in both cases, we take the dot product of u with the direction vector, v divided by the magnitude of v, which is only the direction of v. It's the unit vector for v. And for the projection, we go on to multiply the result then by a direction vector. So let's do an example of finding a vector projection. In this example, we're going to find the vector projection of a force, F, noted in component form 5i plus 2j, onto the vector V, noted in component form as I minus 3j. And we're also going to find the scalar component of F in the direction of V. Recalling what we just defined regarding the projection of U on the vector V, we have this formula given here. The projection of U onto V is U dot V divided by the magnitude of V squared times V. So in this case, we're dealing with F and V. This would be the projection of F onto V. That would be F dot V divided by the magnitude of V squared, then times V. If you recall properties of dot products from the previous video, one thing that we noted is that the magnitude of V squared is equal to V dot V. So for that calculation, we may be able to shorten it by doing V dot V instead of finding the magnitude and squaring it. Either way will both work. So I'm going to do some calculations. I'm going to do F dot V. F dot V is going to be 5 times 1 plus 2 times negative 3, which is 5 take away 6, or negative 1. I'm going to calculate V dot V, which is 1 times 1 plus negative 3 times negative 3, which is 1 plus 9, or 10. And then I'm also going to calculate the magnitude of V. And the magnitude of V is the square root of 1 squared plus negative 3 squared, or rather the square root of 10. And you'll see the square root of 10, that magnitude of V, the square root of 10 squared, is equal to 10. So that proves that that property of dot products is true. So in this case, the projection of F onto V is F dot V, negative 1, divided by the magnitude of V squared, 10, which is, of course, V dot V, times the vector V. And the vector V that was given is I minus 3j. So here I'm going to have I minus 3j. Or rather, the projection of F onto V is negative 1/10 I plus 3/10 j. And lastly, the scalar component of F in the direction of V is going to be the magnitude of F times cosine of theta, which is F dot V over the magnitude of V, or F dot V being negative 1, magnitude of V, root 10. So that is the scalar component of F in the direction of V. In this video, we discussed and learned about the projection of vectors, and we calculated some vector projections, projecting one vector onto another.